Let's do an example, a nice example for maximum likelihood estimation, where we have a coin with unknown bias and is flipped until the first head appears. And this procedure is repeated 3 times. So I take the coin, I flip it, I count how many flips occurred until the first head appears. I do that whole thing 3 times. The first time it took 2 flips to see the first head, next time it took 5 flips to see the first head, and the last time it took 4 flips to see the first head. Find the maximum likelihood estimate for P, the probability of heads on that coin. All right, so in this context, what we have really is a sample of values 2, 5, and 4, values of a geometric random variable, because a geometric random variable counts the number of trials until the first success, or we have a series of repeated independent Bernoulli trials. And that's what's happening here. So here we have a sample x1 equals 2, x2 equals 5, and x3 equals 4 from a geometric distribution from, let's say this. So that's the usual notation for, you have this distribution you're sampling from, you just use capital X for the random variable of that distribution, and use x1, x2, x3, and so on to represent random variables for the first sample value, the second sample value, the third sample value, etc. So this idea of maximum likelihood estimation is to actually write down the probability of getting these sample values as a function of P. And our maximum likelihood estimate is going to be the value of P that makes getting a sample like this as likely as it possibly can be. That's the sort of philosophy of maximum likelihood estimation, is the thing that occurred, let's find the value of the parameter that makes that thing that actually occurred as likely as possible, since it's something that actually happened. So, right, let's do that. So for a geometric random variable, remember, you have the PMF, which is like this. Looks like 1 minus p to the power x minus 1 times p. Remember, you can think of this as if you had to do x trials to get the first success, then you had x minus 1 failures and then 1 success on the end. So this is if, x is in the set 1, 2, 3, etc., and 0 otherwise. Okay. So the actual probability of getting a sample like this, you can write that down. That's called the likelihood. So this likelihood, this squiggly L, what I'm going to write here is the probability of getting these sample values given P, the value, a value of the parameter P, which this is going to be our variable. So if you think about this, we're just going to take the probabilities of getting each of these things, and we're going to say this happened, and this happened, and this happened, and these were all sort of independent, run-throughs of this procedure. So we're going to take the probability that it took 2 flips to get the first head, the probability that it took 5 flips to get the first head, and the probability that it took 4 flips to get the first head. And we're going to say that happened, and that happened, and that happened, and these things are independent, so we're going to multiply the probabilities. All right, it's very important that we're taking a simple random sample to make that true, because we're assuming that the fact that there were 5 trials before the first head in the second run-through of this experiment doesn't change anything about any of the other run-throughs of this experiment, right? Okay, good. So let's write this down. So in general, this likelihood function, what is it? Well, when you want to get the probability that it took 2 flips to get the first head, that's exactly what this function tells you, right? This is BMF. So that's fx at 2. That's the probability that our random variable takes the value 2, which means that 2 2 flips occurred, right, before the first success. And we're going to take the value of the PMF at 5 and at 4, and we're just going to multiply them. That's the likelihood. So, in maximum likelihood estimation, we're just trying to, in these things, you'll see once I actually plug these numbers into this PMF, there's going to be, the variable p is going to be in here. I'm trying to find the value p that makes this expression as big as it possibly can be. You can also maximize the log likelihood. This is usually the more common way to do it, because oftentimes when you go to do the finding a maximum, the typical way to do that is with calculus. You take the derivative, and when you take the derivative of a product, it takes a lot of work. Whereas if you ln this thing, you will see, if I just ln this thing, fx at 2 times fx at 5, fx at 4, then you can rewrite that as ln of fx at 2 plus ln of fx at 5 plus ln of fx at 4. So now we have lns, which makes it more complicated, but on the other hand, we've made this product into a sum, which is nice. For the purposes of taking the derivative, when you can just leave these plus signs where they are and take the derivative of each of these pieces by themselves, which can save you a lot of work. And remember that to maximize any quantity, you can maximize ln of that quantity because ln is an increasing function. So if you're choosing the biggest value of something, then the input where that occurs will also give you the biggest value of ln of that thing. The same input will give you the biggest value of ln of that quantity. You probably did that in Cal 1 with maybe squaring and square rooting to make calculations easier. That's pretty common. But ln, you can also do it with any increasing function. That's true. So we got our log likelihood. So let's write this out. And here we go. So I should say, when you're actually doing one of these, usually you ignore this step. Oftentimes you just skip straight to the log likelihood. Sometimes it's easier this way, but a lot of the time it's easier this way. So let's actually plug everything in and figure this out. So we have 2 goes in for x, so that gives us, what's fx at 2? 1 minus p, 2 minus 1 is 1 times p. Plug in the 5, 1 minus p to the 4 times p, and plug in the 4, 5 minus 1 gives 4, and here, 4 minus 1 and 6 1 gives you 3, and times p. All right, so there we go. That is the log of the probability of obtaining this sample. If you just put any value you like for p, this parameter, this probability of heads, and you compute this, what is it? It's giving you the log of the probability of getting the sample you actually got. So we want to make that as big as we possibly can. So we're going to take the derivative and find the critical points, maximize the way you did in Cal 1. But right now I'm going to simplify it first to make taking the derivative easier, because we're going to have to do the chain rule and the product rule, and it's going to take a long time. So I'm going to break everything up using logarithm laws as much as possible to make the derivative easy. So let's see. Remember, you can turn a logarithm turns a product into a sum in the following way, like this. So this term right here, ln of 1 minus p times p, becomes these two terms, ln of 1 minus p plus ln of p. And now I can break this one up in the same way. And also remember, if you have ln of a power of something, you can bring the power in front. So when you do that, you'll end up with 4 times ln of 1 minus p plus ln of p. Right? Because this gets broken up into two terms, ln of 1 minus p to the 4 and ln of p. There's ln of p. And the ln of 1 minus p to the 4, I took the 4 and I brought it down in front. And similarly for the last term, I'll end up with 3 times ln of 1 minus p plus ln of p. All right, and now putting everything together, what do we have here? Ln p, ln p, ln p. We have 3 times ln of p plus, look at all these ln 1 minus b's. How many do we have? 1 here, 4 here, and 3 here. I guess we have 8 in total. 8 ln 1 minus b's. So there it is. Now this is going to be pretty easy to take the derivative of, so I'm going to do that. So to find the maximum value here, I'm going to take the derivative. So the derivative, we started with this thing called L, which was a function of P. So I'm going to call the derivative dL by dP. Using this, Leibniz notation. L is the function I'm finding the derivative of. P is the variable I'm taking the derivative with respect to. And the function was 3 ln P plus 8 ln 1 minus P. So P is my variable here. The 3 is going to stay where it is. The ln of P is going to turn into 1 over P. The ln of 1 minus P, I got to use the chain rule. It's going to turn into 1 over 1 minus P times the derivative of 1 minus P, which is negative 1. So we're going to get 3 times 1 over P plus 8 times 1 over 1 minus P times negative 1. I did that right? I think that's good. And so we have 3 over P plus, minus, it's the minus 1, 8 over 1 minus P. Great. And remember here, this P is going to represent the probability of heads. So really we're finding the maximum value of this function on the interval 0 to 1, even on the open interval 0 to 1. In fact, if you were to try to plug in 0 here or 1 here, you would see one of these would be undefined. But that's fine, we're not worried about that because our estimate for P, it's going to be something between 0 and 1. Obviously, it can't be 0 because a head actually occurred, and it can't be 1 because a tail actually occurred. Maybe that's not a very good reason because events with probability 0 can occur, but here it occurred in a finite number of trials every time. It's easy to convince yourself that the P should not be 0 or 1 because we're trying to make the probability of getting this sample as big as possible, and I don't want it to be 0. 0 is not going to be the biggest I can make it. There's going to be values of P where the probability of getting a sample like this is bigger than 0. So I can safely ignore the values P equals 0 and P equals 1. So I'm maximizing this function on the open interval 0 to 1. Cool. All right. So are there any critical points on this open interval from 0 to 1? Well, let's set this equal to 0 and see. There's no critical points where it's undefined because those occur just when I get P equals 0 and P equals 1. And we just talked about that. We're not worried about those. We're only concerned about critical points in the open interval 0 to 1. So let's set this equal to 0 and see what we get. We get 3 over P equals 8 over 1 minus P, right? And then 3 minus 3P equals 8P. And all in all, you get 3 equals, what? 11P? So 3 over 11. So you get a critical point at 3 over 11. And that is going to be our maximum likelihood estimate for P. We still have to convince ourselves it's actually a max, like it maximizes the probability. So there's a few ways you can do that. Remember from Cal 1, you can do the first derivative test or the second derivative test. So for the first derivative test, that's f dt. Remember the idea of the first derivative test is you say, okay, I'm interested in values between 0 and 1. I don't care about anything out here. I found a critical point, 3 over 11, which is somewhere around here, maybe. And then to convince myself that there's a max here, one thing I can do is I can evaluate this derivative at some point smaller than 3 over 11 and some point bigger. So maybe I'd evaluate this at p equals maybe 2 over 11. Remember this notation, the derivative of L with respect to p evaluated at p equals 2 over 11. If you were to do that, I'm not going to do it, you would see that it's positive. So just take this thing right here, this derivative, and just plug in p equals 2 over 11. And I don't care what it comes out to be, all I care is that it's positive. You can check that. On the other hand, if you were to do dl by dp and take a value like p equals 4 over 11, something on the right-hand side of 3 over 11, you would see that it comes out negative. And so the idea is this function, L, is going up on this interval, and it's going down on this interval. Because the derivative measures the slope of the graph. The slope of the graph comes out positive, that means the function is going up. The slope of the graph comes out negative, the function is going down. And so indeed, this point right here is a max. Great. The other way to check that this gives a max is to do the second derivative test. And the idea of the second derivative test is to compute the second derivative. And if the second derivative comes out negative, and you found a point where the first derivative is 0, what that means is you've got a point where you've got a horizontal tangent, but where the function is concave down. So that's going to be a max. This is going to be what happens if our second derivative, d squared L by dp squared, comes out negative. On the other hand, if the second derivative comes out positive, the function is concave up. And so this is going to be the situation when d squared L by dp squared comes out positive. So to check that this gives a max, we should take the second derivative and check that it's negative in this region of interest. So let's do that. This is often sort of it turns out that it's often pretty quick to do this in a lot of these maximum likelihood estimation problems. The second derivative doesn't take that long to get. You often get simple things like this. So in order to do that, let's actually rewrite the first derivative in a way that makes it faster. So dl by dp. I'm just going to write this putting the p in the 1 minus p in the numerator. So 3p to the power minus 1 minus 8 times 1 minus p to the power minus 1. And that way I can just use the power rule and the chain rule. And to get the second derivative, so here we go, d squared L by dp squared minus 3p to the minus 2 minus 8 times minus 1 minus p to the minus 2 times minus 1. This is minus 1 right here is from the chain rule, right? So, after all that, let's see what this works out to be. Minus 3 over p squared for the first term. And for the second, it's under 3 minus signs. So minus is 8 on top. And then 1 minus p squared in the denominator. Right? Because I got one negative sign in here, that's there. 1, 2, 3 on this term, it's there. And now if you look at this, what is this? This number is negative. Because the numerator is negative, the denominator is positive. Remember, we only care about values between 0 and 1, the open interval 0 to 1. And so, anyway, it's a square, so it's positive. And the point is I can't divide by 0. I don't care about that because I don't care about the case when p is 0. Same deal here. So both of these terms come out negative all the time for any value of p I can try and put in. So that's negative. So therefore this function, the likelihood function, the log likelihood function, in fact, is concave down. And so we're in this situation, so we get a max. Great. And so to finish the problem, we can say, thus, the maximum likelihood estimate for p is p hat equals 3 over 11. Perfect. Remember, this hat denotes an estimator or an estimate. So it's 3 over 11. Cool. Our estimate for the probability of heads on this coin. One more thing. What we did there was we found the maximum likelihood estimate, which is a number. And remember, the maximum likelihood estimator is a function. So now let's find the maximum likelihood estimator. Find the maximum likelihood estimator for P. So what this means is that instead of starting with a particular set of sample values, 2, 5, and 4, I'm just going to do it in general. So call this x1, x2, and x3. So now, our sample values, so take a simple random sample, x1 equals little x1. It could be anything. Whoops, where's my eraser? x2 equals little x2, so on, all the way up to xn equals little xn. So I have n sample values that I don't know what they are. And what I want to point out is that I can do exactly the same thing. I don't need to know what they are. The process is just as easy. So now when I find my log likelihood, instead of having 2, 5, and 4, I'm just going to have these unknown sample values, x1, x2, up to xn. So my log likelihood is going to be the likelihood of obtaining this sample, give it p, x1, x2, xn. And just like before, it's going to be ln of fx of x1, and I'll write it as a sum, plus blah blah blah, plus ln of fx xn. So now this can look difficult because I got a lot of variables, but remember that these variables right here, they're not actually variables. You can treat them like constants, because when we go to take the derivative, we're varying the value of p. We're saying what value of p makes this sample as likely as possible. So we're taking the derivative with respect to p. These values are just the sample values that we saw. So they don't change. Think of these as some fixed unknown values, whereas p, we're moving it around to see what makes the probability of getting that sample as big as it can be. So if you write these out, you will get ln of, looking back at the BMF here, the only difference between this and this, here we have an x, here we have a little x, here we have a little x1. So it's just going to use this with the little x1. So 1 minus p to the little x1 times p, plus, I'll do the second term as well, 1 minus p to the little x2 p, plus blah blah blah, last one, 1 minus p to the little xn times p. And you'll see from now on it looks really just like what we've done. Instead of the 2, 5, and 4, we'll have x1, x2, and xn. But the same thing will happen. We'll break this up using logarithm laws into x1. Oh, sorry, I forgot the minus ones. So each of these have minus ones. Apologies for that. So we'll break this up into x1 minus 1 times ln of 1 minus p plus ln of p. So all that came from the first term. Remember, we broke it up into 2 terms and then we moved the exponent down. Plus, let's not write the second term because I'm going to run out of space. All the way up to xn minus 1, ln of 1 minus p plus ln of p. Okay, so in total, what do you get here? How many ln of p's do you have? Well, for each one of these guys, I get a ln of p term, and there are n. So I have n ln of p's. And let's look at the ln of 1 minus p's. What's in front of them? x1 minus 1, x2 minus 1, x3 minus 1, all the way up to xn minus 1. So it looks like you have something like this. x1 minus 1, x2 minus 1, all the way up to xn minus 1 times ln of 1 minus p. All right? This ln of 1 minus p is a common factor in all the other terms. All the ln 1 minus p terms. Cool. Okay, so what's in here? It looks like I got n ln p plus, you can add up all the minus ones together, maybe to make this look a bit nicer. So put all the x's together and put all the minus ones together. minus 1, minus 1, minus 1, n times. So you get minus n. Great. And now we can take the derivative. So dl by dp. And again, this sort of looks intimidating because of all the variables floating around, but this is just a giant constant. Taking the derivative of this is easy because this is a big constant. So the ln of p becomes a 1 over p. This big constant is times ln of 1 minus p, so this just stays where it is. And this ln of 1 minus p, 1 over 1 minus p, times negative 1 by the chain rule. Okay, and so just like before, if we set this equal to 0, we can solve for p x1 plus x2 plus blah 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 up to xn minus n over 1 minus p, and I forgot about this negative 1, didn't I? It to be minus here. All right. And solving this real quick, you have n over p equals the sum of all the xn's minus n over 1 minus p. So you have n minus np multiplying across equals p times this thing. Right, and to finish this off, let's look here. What do we have? Oh, okay. Notice that when I multiply, I can actually do this here, right? Because check this out. I have a minus np on this side, but then when I expand this out, I'm going to have a minus np on the other side. So this and this are going to go away. Because here I have an np, and here I have an np. And they're both negative, so I can just add np to both sides. Then I end up with n equals p times. So n equals p times the sum. And so therefore, p equals n divided by that sum. There it is. So in general, the maximum likelihood estimator, if we write it out, looks like, oh, and by the way, I should also show that this gives a max. I can do it in the same way as before. If you take the second derivative of this guy, yes, it has this big constant, but it would look exactly the same. You'll just get different constants. But in terms of evaluating the derivative, it's still easy because you still have p to the minus 1 here, 1 minus p to the minus 1 here. And the derivative is going to go the same way. You just have bigger constants. And once again, you'll be able to show that the second derivative comes out negative all the time. Cool. So therefore, and you show it gives a max by the second derivative test. So therefore, this is your max. So that's your maximum likelihood estimator. Once I replace these, because these are real number variables right here. So technically, to be an estimator, I should replace these with random variables. This right now is a number. These are real number variables. So thus, in the end, the maximum likelihood estimator, which is normally denoted MLE, for P is P hat equals N divided by my sample values, the sum of my sample values. And notice that that is indeed what we got before, right? Because in our original problem, our sample values were 2, 5, and 4. And so if you add them up, 2 plus 5 plus 4, what do you get? 11. And n, the number of sample values, 1, 2, 3. So n is 3, and the sum of the sample values themselves is 11. So yeah, 3 over 11. And that is what I came up with. Yeah.